Hello, this is Dr. Benjamin Norris from the Chemistry Department at Frostburg State University. Today we're going to talk about valence. The molecule on the right is ethanolamine. Ethanolamine is a water-soluble organic base that is used in gas scrubbers to remove carbon dioxide and other acidic gases from gas streams. I've chosen ethanolamine today because it shows the four most common elements found in the structures of organic molecules and their most common bonding patterns. Carbon typically has 4 bonds, nitrogen typically has 3, oxygen typically has 2, and hydrogen can only form 1 bond. This typical bonding pattern is an example of the valence of these atoms. Valence represents the optimum or maximum number of covalent bonds that an atom of any element can form without possessing formal charge. Atoms can be described as univalent, divalent, trivalent, tetravalent, and so on based on the number of covalent bonds that it can form. For example, an element whose atoms can only form 1 covalent bond would be described as univalent. Examples of univalent elements are hydrogen and the halogens. If the atoms of the element can form 2 bonds, they're called divalent. Oxygen is an example of a divalent element. If atoms of that element can form 3 covalent bonds, they are described as trivalent. Boron and nitrogen are examples of trivalent elements. And if the atoms of those elements can form 4 covalent bonds, we describe them as tetravalent. Carbon is an example of a tetravalent element, and because carbon is the most common element in organic chemistry, we'll spend a lot of time talking about carbon and its 4 covalent bonds. You may remember the term valence from general chemistry, where you talked about the valence shell electrons, those electrons in the outermost energy level of an atom. Valence electrons are those electrons available for chemical bonding, and so the idea of valence between organic chemistry and general chemistry is complementary. We're talking about the electrons available to form covalent bonds. As I just mentioned, hydrogen atoms are univalent. Hydrogen atoms have 1 electron, and that electron is in the first energy level, and that electron is hydrogen's only valence electron. Hydrogen can use that 1 electron to form a covalent bond with atoms of itself or other elements. An example of a molecule where hydrogen atoms are forming 1 covalent bond per hydrogen atom is H2, or dihydrogen. Halogen atoms are also univalent. Even though fluorine and other halogen atoms have 7 valence electrons, there is only one of them that is unpaired, and so there is only 1 covalent bond that can be formed between fluorine and another atom. An example of a molecule containing fluorine and 1 bond connected to that fluorine is hydrogen fluoride. Oxygen atoms are divalent. Oxygen atoms have 6 valence electrons, and when we draw the Lewis symbol for oxygen, we indicate that 2 of those electrons appear to be unpaired. Those unpaired electrons are the ones that can be used to form covalent bonds, and oxygen can form 2 of them. An example that you might be familiar with is water, in which the oxygen atom forms 2 covalent bonds, 1 with each hydrogen atom. Nitrogen atoms are trivalent. The Lewis symbol of nitrogen contains 5 valence electrons, 3 of which appear to be unpaired. Those 3 electrons can form 3 covalent bonds. One of the simplest molecules of nitrogen is ammonia, which has 3 covalent bonds to hydrogen. Boron atoms are also trivalent. Boron has 3 electrons in its valence shell, and each of those 3 electrons appear unpaired in its Lewis symbol. Boron can use each of those 3 electrons to form a covalent bond. One molecule that has 3 covalent bonds to boron is borane, BH3. Borane is a little bit of an anomaly because the boron only has 6 electrons around it. You might remember from general chemistry that boron is allowed to break the octet rule. Carbon atoms are tetravalent. Carbon has 4 valence electrons, and in its Lewis symbol, those electrons appear unpaired. Carbon can use each of those electrons to make 1, 2, 3, 4 covalent bonds. Methane, CH4, is an example of a molecule where carbon is forming 4 covalent bonds. Ions can be an exception to these valence patterns I've just talked about. If the central atom in a molecule has a formal charge, it may have more or fewer covalent bonds than you would otherwise expect. For example, if you remove a hydrogen atom from methane, you might end up with the methyl carbocation. Cations of carbon are trivalent. They only have 3 covalent bonds. If you take the lone pair from ammonia and replace it with another bond, you get the ammonium cation, which is tetravalent. If you add another bond to hydrogen to borane, you get the borohydride anion, which also is tetravalent. Finally, and if you take one of the hydrogen atoms away from water and convert the covalent bond into a lone pair, you get the hydroxide anion, which is univalent. Generally, if you replace a lone pair with a new bond, you go from your valence increases by 1. If you replace a bond with a lone pair, your valence decreases. If you previously had no lone pair and added a bond, your valence also increases. We'll talk about these bonding patterns and their relationship to formal charges again in an upcoming video. Another exception that you might recognize from general chemistry are those atoms which can be hypervalent. Hypervalent atoms are atoms of elements that can have multiple valences. You might recognize them from general chemistry as those atoms which were allowed to exceed the octet rule. One common example was sulfur, and I'm showing 3 different dimethyl compounds of sulfur atoms that have 2 methyls or 2 CH3 groups attached to them. The first one here is dimethyl sulfide, and sulfur, like oxygen, which is above it in the periodic table, is divalent. But sulfur can form additional compounds with further bonds, such as dimethyl sulfoxide, a sulfur with 2 carbon groups and a double bond to an oxygen, or dimethyl sulfone, 2 carbon groups attached to the sulfur and 2 oxygens both doubly bound. So sulfur can have a valence of 2, 4, or 6. Generally, those elements in the 3rd row of the periodic table and below can be hypervalent, and their valence increases by 2 each time. We can use information about valence to establish common bonding patterns for the common elements in organic compounds. For example, carbon is tetravalent. In addition to the 4 single bond pattern that I have been showing up to this point, carbon is capable of a total of 4 different bonding patterns. The 4 single bond pattern is incredibly common and is found in molecules like methane. Additionally, carbon can form a bonding pattern where it has 2 single bonds and 1 double bond. This pattern is found in molecules like formaldehyde. Carbon can also form a pattern with 1 single bond and 1 triple bond, which is found in molecules like hydrogen cyanide. Lastly, carbon can form 2 double bonds, found in molecules like carbon dioxide. Other tetravalent atoms also can form bonds using these bonding patterns. For example, nitrogen with a positive charge and boron with a negative charge are both tetravalent and can both form bonds using these patterns. Trivalent atoms likewise have additional bonding patterns besides the 3 covalent bonds that I have shown. In fact, trivalent atoms have 3 total bonding patterns. So for example, nitrogen can form 3 single bonds as it does in ammonia. It can form a double bond and a single bond, as it does in nitrosomethane, and it can form one triple bond, as it does in acetonitrile. Other trivalent atoms also form bonds in these same patterns. For example, the carbanion and the oxygen cation are both trivalent with a lone pair and form bonds using these patterns. The other trivalent atoms, carbon with a positive charge and boron, also form bonds using these patterns. They just would not have the lone pairs associated with them. Divalent atoms, like oxygen, can form two bonding patterns. Oxygen can form two single bonds, as it does in water, or one double bond, as it does in formaldehyde. Other divalent atoms are also capable of these bonding patterns, including nitrogen with a negative charge. Lastly, univalent atoms are relatively boring. They can only form one bond, and they can only do that in one way. Hydrogen can form one bond, as it does in H2. Oxygen with a negative charge can form one bond, as can all of the halogen atoms. Up next, we're going to talk about representing organic structures using condensed structures. Thank you for watching.